This is Group 9 video presentation for our capstone project. The goal of the project is to develop a detailed design for the Eric J. Barnhill building. Load, structural alternations and sizing, structural system and components, and finally sustainability will be discussed throughout the video. The materials used throughout the design process were selected to optimize the construction budget and maintain the building's sustainability, safety, and integrity.
Now about the structural changes we made. The main thing we changed was removing this overhang on the east side of the building. This needed a lot of materials to hold up. It would have been very expensive, involved some complicated calculations, and it only gave about 3% more floor area over our solution. In our redesign, we moved the sides closer together and got rid of that overhang. In addition to that, we reduced the height of a few floors so that they were more consistent. We removed the middle floor on the first level, and we made a few other minor changes to simplify the design.
In this project, we carefully considered loading to ensure safety and stability of the structure, from which we came up with the following dead load level tables as well as the load combination provided per CE448W guidelines to account to the potential worst case scenarios. Through calculations, we determined further loads such as wind loads, seismic loads, and snow loads, and gathered all the information we had to create the drawings seen here, which is a live load layout for a typical floor within our structural building.
After the material definition and calculating the load, they are applied in SAP 2000. The model has been created with an initial frame sizing. The model is then tested and refined using AISC tables and diagrams to resize the frames and change the layouts if necessary. This was done to reach a suitable model in terms of sustainability and safety, so we use a small sizing of the member that can handle the load. The model was also tested for wind deflection, so that it won't deflect above the limits defined by ASC code. After finishing the model in terms of sizing and layout, the results of the load that the members experience are extracted. They are used to design the special components of the model. These are connections, splices, cassette plates, base plates, and footings. These components are designed based on appropriate codes and then drawn using AutoCAD. The design functionality of these components are confirmed using associated softwares like RAM connections.
So now I'm going to talk briefly on the sustainability of the project. On the rooftop, we were able to fit 92 lightweight commercial solar panels, all while avoiding the off-limits area shown in the image to the left. Vegetation will also be added around these panels, along with the improvement of the vegetated roof on the strip located a floor below. We also wanted to implement a commercial dual-fuel generator, which will primarily run on natural gas and switch to diesel fuel if needed.
SAP 2000 warns of KLR ratio over 200 on some beams. Adding stiffeners will help in reducing the risk of buckling. We recommend confirming load behavior on composite beams with softwares like ETABS. Also, design assumes full shoring during construction, so adjust the weights if not fully shored. We recommend consulting a solar expert for optimal panel pitch and direction. Consider contracting a graduate student or professor if no solar professional is available.
This is the end of the video, and thank you for taking the time to watch our group's video presentation.